late, but that's okay. So welcome everybody to the spring semester GGE seminar series. And today we have Doug Goetz, who was a graduate of our department in environmental science. Remind me what year that was?
I think 2009.
2009, yeah. Okay.
Mm-hmm.
And maybe you could just share with us quickly sort of your career path after that, because it's nice for students to know sort of what their opportunities are, and then we'll get right into your talk.
Sure, yeah. So in 2000, I graduated winter of 2009. I took about like a year or two, year and a half off. And then I went to grad school at Drexel University in Philadelphia. In their environmental engineering department there. And I started just as a master's student, but then got involved with one of the professors there and became a PhD student in working on looking at emissions from, methane emissions really from natural gas extraction in Pennsylvania. And so I did that for a few years, and then I did some other emission work looking at aerosols from in Nepal and then also in Antarctica. And then I started my postdoc here out in Colorado in 2017 at this lab that I work at now. It's called the Laboratory for Atmospheric and Space Physics. And it's a research lab that's affiliated with the University of Colorado in Boulder. And I started working on this project I'm going to talk to you guys about today, which is Stratosphere 2, which is a superpressure ballooning project. And then I've had a bunch of other projects that have happened or are in the process of happening since I started. I became a full-blown research scientist here, last April, I guess, or last March, something like that. So, and
cool.
Yeah.
Weren't you in a massive earthquake in Nepal?
Yes, so the 2015 earthquake in Nepal, I was there doing field work for like 2 months, and I was supposed to be there for 2 months, but it got cut short by a month because of the earthquake. So, yeah.
Wow, that must be a very interesting story.
Yeah, it's
for another time
for sure. Yeah. I will say I didn't feel the earthquake, which is surprising, because I was in a van on a very bumpy road, and so I just thought it was another bump in the road. But we got stuck behind a rock slide actually on this mountain road, there's a whole story behind it. But yeah, wow. It was quite the experience.
Yeah. Okay, so so do you want to share your screen or that, and then we'll get started? Everyone. In the past, if people had questions, Doug, are you comfortable with them speaking up and interrupting you?
Yes, please do. I mean, I am not the biggest fan of monologues, I guess. So please, if you have any questions, just interrupt me at any time, and I'm happy to, to make more of a dialogue, I guess. So.
And then if people have questions at the end as well, we can.
Exactly. Yeah.
Okay. Perfect.
Cool. Okay, so you guys can see my screen, I assume?
Yes.
And can you see my mouse? Because that's also going to be kind of important.
Yep.
Okay, cool.
Working. Yeah.
Okay, so today I'm going to talk to you about the Stratosphere 2 project. I titled this Exploring the Tropical Gateway to the Stratosphere with Superpressure Balloons. This is one of several projects I've worked on in the last few years, and really is, kind of my baby that I've been part of for, for what, 3 or 4 years now. And what's really great about this is one of the few international field missions that is still ongoing and really hasn't been totally affected by COVID, where some other projects I've been involved with have. So let's see here. There we go. So I'm gonna, just a quick outline here. I'm gonna give you a brief introduction to scientific ballooning, because that's a big part of what I do now. Then talk to you about Stradiol 2, give you the background of it, and then talk to you about this field campaign that happened in 2019 from the Seychelles. So high altitude science. You guys might not know it, but balloons are really important to making measurements in the atmosphere. And, just looking at the slide here, there's pictures of a bunch of different, platforms, but all of these really throughout history and maybe in the last 100 years have been used to make measurements in place in the atmosphere, so in situ measurements. And they're really unique measurement platforms because they get to places that you really can't in any other way. Like this balloon, for example, this small balloon on the left here, that reaches somewhere around 100,000 feet in the atmosphere, about 3 times as high as a plane flies. And so, this is something that really can't be done with planes or any other method. And all of these balloons, they operate using the same sort of principles, and it's all based on buoyancy. So, so this guy Archimedes, all the way back in 250 BC, he really first described how balloons operate, and this is, and he basically said any object immersed in a fluid is buoyed up by a force equal to the weight of that fluid that's displaced. So in other words, if you have a volume of air, say it's helium or hydrogen or methane even, and it's trapped inside of a balloon, well, it's going to be buoyed in the atmosphere, and that buoyancy is going to be dependent on the volume that is displaced. So the more volume displaced, the more force that you're going to have to actually go up into the atmosphere. And what Archimedes didn't have, though, is that this is really a balancing process of, well, yeah, there's force, but if you're talking about like a ship on the ocean, it has buoyancy, but the weight of that ship also matters of how buoyant it is. And so that's the same with balloons. So whenever we're doing any type of ballooning, we're trying to balance this upward force, buoyancy force, with the force of our load. So, and that load is, the mass of the fill of the balloon. So helium and hydrogen have mass, and that actually weighs down on a balloon, the weight of the balloon itself, and then ultimately our payload. But what's really important here is this volume term when talking about ballooning, so this V. And so just to give you an example here, there's, we have 2 balloons on the right, okay? And these are actually launches I did a couple years ago, one from Wyoming and one from Boulder. And these are 2 types of scientific balloons. There's a rubber balloon and this is a plastic balloon. And what you'll notice is the one on the right, for example, isn't fully inflated. It kind of just looks like, sad little, I don't know, like a sea creature or something. And so the reason for that is because that volume is going to expand as it goes up into the atmosphere. So on the left here, we have a figure of pressure or altitude versus pressure that's from actually this launch in 2018. And what you'll notice is, pressure decreases as you go up into the atmosphere. And so that volume is actually going to expand, and this is just a diagram of, simple diagram of what's happening, where your balloon volume keeps expanding as you go up into the atmosphere. Now, the thing that you'll probably realize is that it can only expand so much, and it in fact does, and it'll burst when it reaches a certain altitude. And this is actually, these are great pictures right here. This is a rubber balloon bursting at altitude, and this guy, Patrick Cullis, he has a bunch of really cool ballooning photos. I recommend going to this website at some point to check out some cool photos, high altitude photos looking at the Colorado mountains and things like that.
How does he take those photos, Doug?
Yeah. So he's kind of he's kind of a famous photographer. He had article in the New York Times showing these similar photos, but the actual, he takes, you know, like digital SLR photos of the ground level or looking at the ground, and it's really beautiful. So yeah, and so what this is actually called here is this is a type of balloon that's very common around the world, and this is a sounding balloon. And so what we're doing with these balloons, if we have some sort of payload on it, is we're making measurements sounding through the atmosphere, and then it bursts and the instrument comes back down. And, you know, these happen all around the world. So, you know, the most common type of, you know, soundings are meteorological soundings. And basically they have been operating the same since the early 1900s until today. The instruments have changed, but what you're doing is you're taking a you know, small rubber balloon, and you're taking a very light payload that measures pressure, temperature, relative humidity, and take spatial measurements, and you know, probing the atmosphere. And so, you know, this figure on the right here is, I borrowed this from NOAA, a NOAA website, and it's just showing, you know, how common you know, atmospheric soundings are throughout the world. So all the way from the 1940s, where, you know, they sort of just had it in more populated areas, until today, where, you know, the entire globe makes these meteorological measurements with balloons. And in fact, I was down in Antarctica in 2019, and here's a picture from same thing from McMurdo Station in Antarctica. And there's somewhere around, I guess, about 500,000 balloons that are launched just like this around the world every year. And this is the type of data you would get from these meteorological soundings. So, you know, just a quick rundown would be, you know, temperature on the bottom axis with this right, just worry about this right line is temperature. As a function of pressure, and then wind direction and wind speed of that balloon. But then, and this is, you know, sort of what I'm leading to here, is what if we don't want that balloon to burst? And what if we want to actually, you know, measure one layer of the atmosphere, you know, for an extended period of time? And so for this, we need to control our volume. And there's two different methods that are used here. One is what's called a zero pressure balloon, and the other is what's called a superpressure balloon. So zero pressure balloons, you know, another name for them could just be vented balloons. And they're pretty interesting because they're used a lot as test beds for sort of testing satellite sensors and telescopes that are going to go into space, things like that, because they can carry very heavy payloads and stay at one altitude. So, you know, this is just a little diagram from this Super Tiger campaign. It's a NASA campaign that was happening down in Antarctica, I think 2018, somewhere around there, where they're testing a satellite sensor that is going to look at cosmic ray particles. And you can see the size of this thing. I mean, it's huge. And when it's inflated, it's, you know, multiple planes would fit inside of this balloon. And the payload was somewhere around like 5 tons, I think. But then it can also be smaller. So actually just 2 weeks ago up in Laramie, Wyoming, I launched this little payload here. It's about 30 pounds on a zero pressure balloon. And, you know, we launched from Laramie over here and flew at a float altitude of about 19 kilometers, or what is that in feet? Like 60,000 feet. or twice as high as a plane flies. And this balloon floated at that altitude for 3 hours, and then it was cut down, came down on parachute, and went about somewhere around 200 miles downwind of Laramie, Wyoming. And so, but the trouble with these zero pressure balloons is, in theory, you could go as far as you wanted downwind at a certain altitude because you're vented, the volume's the same. But the trouble is that the sun actually heats up the balloon. So you have something like this where during the day, you actually, you have solar radiation that actually heats the inside of the balloon envelope. The balloon rises, it vents more gas. At night, it sinks, and then you have this ongoing cycle where you eventually just lose so much helium that the balloon will be in the ground. And so that's kind of the downfall of these zero pressure balloons. And in fact, oftentimes they're used in Arctic and Antarctic environments, during either when there's total sunlight or total darkness in either, solstice season, because then they can get, fly for a very extended period of time. But then, and what this study is going to talk about are superpressure balloons. And this is the alternative to zero pressure balloon, where you actually are controlling volume by having a balloon that has, a very thick layer of plastic, and it's at a higher pressure differential than the atmosphere. So then it stays at a solid volume, regardless of the solar cycle. And so, here in this diagram, we have, the white circles are the zero pressure, and then the red circles would be what you'd see with a super pressure, where there's some slight oscillation because the envelope still warms and cools depending on how much sunlight you have, but really doesn't as much. And so what you get with the superpressure is the ability to actually fly for days or months in the atmosphere, and this balloon will just drift downwind. And this picture on the bottom here is just an example of what it looks like fully inflated, and it uses really thick plastic to do it. Here's just an example of the type of oscillations. So this is pressure data from a superpressure flight that I was part of, and you can see these, these blue oscillations in pressure. So, just from a bunch of different, basically buoyancy correction forces and things, these balloons will oscillate, somewhere around like 30 or 40 meters over a 4-minute period, just continuously. So, it's not perfect, but it's much better than what you get with zero pressure.
Doug, what's the difference in cost of launching just like a sounding weather balloon versus one of these things?
Yeah. Well, so just a typical rubber balloon that you would see, with meteorological sounding, they're like in the $100 range. Like you can get one for a couple $100. That zero pressure flight I did from Laramie, that balloon could hold 10,000 cubic feet of helium. So it wasn't that big, but it was still a pretty big balloon in comparison, and it was somewhere around like $2,000. But like these super pressure balloons, they're very expensive. I think they're somewhere around like $50,000 or somewhere around there a piece. So you got to make sure you're doing it right. You can't screw up, So yeah, then these superpressure balloons, the idea behind it's been around for a really long time. These are some papers I found from the 1960s of people had these ideas of, we want to measure at one, altitude level in the atmosphere with these balloons, but really the technology wasn't totally there because of, I think GPS really is one of the biggest reasons for that, or or satellite communications, things like that. And so, you know, more recently, these superpressure balloons have been used in for larger scientific campaigns. So this is back in 2010, and these are people that I work with now. Kness, the French Space Agency, some scientists from France, and then the group I work with now was involved in this campaign where they launched 13 superpressure balloons from McMurdo Station, and it was super successful. They, you know, these things flew around Antarctica, you know, multiple times, and they were able to, you know, get a lot of great information about what they were looking at were polar stratospheric clouds and ozone depletion and the, you know, ozone hole over Antarctica. So, you know, until now with Stradiol 2, that really was the most famous and sort of successful measurement campaign using superpressure balloons. Any questions on ballooning before I move on, actually?
Do you ever have troubles with like flyaways, or is there like a control point?
Yeah. Yeah. You mean like them just sort of having a rogue flight?
Yeah.
Yeah, very much so. Terry Deschler, who is an emeritus professor from Wyoming that I work with, he has this great story about a balloon that they lost back in the 90s from Laramie, and they actually had, you know, the U.S. government was involved and NORAD, because they basically saw this thing, you know, they weren't sure if it was a nuclear missile or what it was, you know, flying through the atmosphere, and they lost it at one point. And then a couple of years later, they found a remnants of it in Virginia. So it's easy to do, but a little bit more difficult nowadays just because of all the different satellite tracking systems that we have, you know, for this. And we also have cut down devices. So if it does go out of range, we basically cut the balloon away, and then it descends via parachute. So
there's a couple questions in the chat. One
yeah.
is, what happens to the debris from the balloon?
Yeah, so unfortunately, that's not always the best story. So, you know, most of the time we try to recover it. And, you know, when we do these larger plastic balloons or rubber balloon flights from here, we go and recover that plastic because, you know, we don't want it to be just out in the middle of Wyoming somewhere, you know, for a rancher to find. But sometimes you can't really help it. So like these zero pressure balloons this Stradiol 2 stuff I'll be talking to you about, I mean, they travel all around the world, and there's really no feasible way to recover these balloons. We had one that landed in sort of war-torn country in Africa in this last campaign. So it was like, wow, we can't really go there to recover. So, but we do recover, I'd say 90% of the plastic.
The other question is, could you clarify what soundings means?
So Doug, it's Dr. B. Nice to see you, Doug.
Yeah, you too.
I just want to talk about this term sounding, because to me that means going vertically up and down. So you could do a sounding of changing in chemistry, rising through the atmosphere. Also, you know, we used to put weights on string over ships to do a sounding of how much water column was beneath it. And geophysically, we do soundings to see the stratigraphy vertically down underneath us at one point. But then you mentioned the pressure balloons. You would try to maintain the same elevation and then go laterally around the planet. Mm-hmm. And I would think of that as a profile rather than a sounding. So just to help bring people along, can you comment on whether I'm using my word sounding correctly and what you think about the difference between verticality and horizontally?
Yeah. I mean, I think you made a good point. I mean, when I think of sounding, I think we're probing the atmosphere vertically. And we still get some horizontal drift, you know, because, you know, if we have a sounding balloon, we go up in the atmosphere, we pop and we come down, and, you know, that might travel 100 miles downwind or 30 miles downwind. So it's not totally, vertical, but what we're talking about with these zero pressure and super pressure balloons really is, it's not sounding. It's not, we're looking at the atmosphere laterally. We want to stay in one layer. And really what we're looking at is this comes into sort of sampling techniques, Lagrangian versus Eulerian. And what we're doing is we're staying with the same parcel of air and we're moving with it. So we're sampling in a Lagrangian way, which is not really, feasible with any other, measurement platform. So does that answer your question?
Yes, sir. Thank you very much.
Okay. Okay, so Stratial 2. This is a mission, multinational mission to study the tropical tropopause layer. And I'll talk more about what the TTL is and the tropical lower stratosphere using long duration superpressure balloons. And on the right here, I just have some, some logos for some of the people involved. This is an NSF funded project in the US here, but it's also a European project with the French Space Agency and some different research institutions out of Paris and different parts of France that are involved. And then, NOAA, US institutions like Scripps.
So there's no US NASA in there.
No, NASA is not involved, as far as I know. No, NASA is not involved. And so, we're looking, what we're really interested in here is the tropical tropopause layer. And before I talk about, the tropical tropopause layer and why we're even interested in it, I think we need some context on what the rest of the atmosphere is like. And so, I pulled up this is from Pittsburgh, actually, from yesterday. This is a atmospheric sounding. This is a weather balloon sounding from yesterday, and then just July 4th in the summertime for context. And so in the mid latitudes, what you see here is, say we're just looking at this black line on the right, and this is temperature as a function of so temperatures on the x-axis, pressures on the y-axis, is that we have two distinct parts of the atmosphere here, and that's the troposphere and the stratosphere. And they're really what makes them different is that the troposphere, it goes from warm to cold. So it goes up to a point, it goes up to the tropopause, and it starts warm, and as you go up in altitude, it cools. And then in the stratosphere, we actually have the inverse, where it's warm and then it goes colder. And it's not as apparent in the wintertime here, as yesterday, where it looks more just like a straight line. But in the summertime, there's definitely a clear inversion in temperature. And this inversion in most of the world actually prevents any transport of air from the troposphere into the stratosphere, especially at mid latitudes and at the poles. And, with some exceptions, of course. But the tropics are very different. So the tropical atmosphere does have transport. And, if we look at this figure on the left, this is just showing the amount of solar radiation that's getting to the Earth in different parts of the world in different seasons. And what you notice about the tropics is that it always gets sunlight. So it's always being warmed by the sun, which makes the atmosphere very active. And it makes it very unstable, creating lots of what's known as convection in that part of the world. And so I really like this figure on the right here. This is showing what's really happening at the equator. So you have a very active atmosphere. You have lots of storms, and that's actually pushing, is creating the circulation pattern where you have transport in the tropics past the tropopause here, and into the stratosphere. And then once it's in the stratosphere, it circulates around the world, typically towards the poles. And don't mind these squiggly lines. I mean, I think that has to do with like wave transport or something like that in the mid latitudes. But yeah, this is a really important mechanism for how different chemicals get into the stratosphere. So if you're talking about water vapor, one of the very important greenhouse gas, how does that get into the stratosphere? How does different pollution compounds get into the stratosphere? How does particulate matter get into the stratosphere? And it's mostly through this gateway at the equator.
Is it like busting through that layer, or is it just wide open, or is it slowly seeping through? Like,
well, that's kind of a topic of debate, and this is one of the reasons why we're making these measurements, is because because of all this activity, it's a little bit different. So it's the TTL, the tropical tropopause layer, isn't as well defined as the tropopause at mid latitudes. So you have a much lower temperature gradient, and let's see, I'll just go into the next slide here. And so looking at this figure, don't even bother looking at this figure on the right just yet. It's a bit complicated even for me. But on the left here, there's a bunch of different transport mechanisms that we're interested in. So overshooting convection. So that's where you'd have a really big storm cloud that would actually punch through this tropopause and transport things into the stratosphere. You have cirrus clouds, which isn't necessarily a transport mechanism here, but is in a sense really important for understanding the radiative balance of the atmosphere. And most of the time, these cirrus clouds, they're actually called subvisible cirrus because they're not really able to be seen by satellite measurements. But then just to answer Julie's question real quick, waves is the other mechanism on how things get into the stratosphere. And so think about this as it's a little complicated because we're talking about 3D space, but think about throwing a rock into like a lake, okay? And you get ripples, across the surface of the lake, but you also get ripples underneath. And so, think of turn that upside down, and you have waves that are going through, that liquid. And it's the same thing for waves in the atmosphere, which are either made from, just being disturbed by mountain ranges or by very large storms, and you create these ripples in the atmosphere. And really, it's a perturbation in density that happens. You're taking one parcel there that's at a certain density and moving it to a different part of the atmosphere.
So are you finding most of this intrusion into the stratosphere near the intertropical convergence zone, or is it more spread out from there?
That's a good question, actually. That would be something, I don't know, actually. You're right. I mean, that area would have the most convection, but it's something to look into for sure. Yeah. I want to go back actually real quick. So, talking about convection in the tropics, I mean, this is an image, and you probably noticed this in the background. This is an image from the Himawari satellite. It's a Japanese imaging satellite. And what you really can see throughout the tropics here is, lots and lots of storms. And this is what's, transporting things into the stratosphere. And in fact, it's somewhere around 10% of the tropics at any given time are covered in storms. Okay, so let's see, we went over this a little bit. Yeah, so the tropical tropopause layer, anyways, it's not really super well defined, and there's still some debate on, what this layer is, how to characterize it, and it's really because it's a transition layer. It has these properties of the troposphere and of the stratosphere. And for this study, Stradial 2, this is something we want to better characterize. So we want to understand how clouds overshoot this layer. Cirrus clouds. Another important thing that I missed earlier is what's the cold point. So this area of the atmosphere is actually really one of the coldest places in the world. So it's somewhere around, depending on where you're at, it's somewhere around -80 to -90 degrees Celsius. And so because it's so cold, what you have is really a threshold where water vapor can't make it through because it dehydrates the atmosphere by causing ice crystals that then fall out. So you have water vapor, turns into ice, and then it falls out as particles or makes clouds. And so to better understand all of these different processes, we need to make measurements of temperature, water vapor, ozone, aerosol in this layer. And we want to do it for a long period of time. And so that's where Stradial 2 comes in. And so the Stradial 2 campaign, or mission, I guess we can say in this case, it's using drifting balloons that are going to fly between 15 degrees north and 20 degrees south latitude. And the plan is to have these up for 90 days. There's 3 campaigns that are involved in this mission. So in 2019, it was November and December of 2019, we had our first engineering flight where we had one of each gondola configuration released from the Seychelles. And then this is really a test of all of our instruments. And then coming up in November of this year is the first science campaign where we have a large number of instruments that are being flown. And then again in 2023, we're doing the same. Just looking at the slide here, it's, how this is really working is we have the French space agency CNES is in charge of the flights. They're in charge of the balloons, balloon operations, launching them. And then we have these French organizations, LMD and Latmos, that provide us these gondolas that we can put our instruments in that are, temperature controlled. They provide power and provide telemetry, satellite telemetry to the ground. And so I've actually here's a table of the different instruments that are involved in flying in these different gondola configurations. And I'm involved with 3 of them, 3 of the US instruments, one that's called Ratchets. This is a water vapor, temperature, particle number profiling instrument. LPC, which is a particle counter, and then Float, which is a temperature profiler, and then the rest of these are really French instruments, with the exception of this GPS occultation instrument. So I'll go into more about this Ratchets instrument and then also Floats. So Ratchets it's a crazy instrument. It's called the Reel Down Aerosol Cloud Humidity and Temperature Sensor. And the idea here is, if you look in the center, is that we have our balloon, we have our gondolas, but then what we have outside of the instrument gondola is a sub gondola that we're calling the Ratchets Profiling Unit. And this thing is actually used to probe different flight levels while in flight. So, looking at this diagram here, we're drifting along in our balloon, just going along at about 10 meters per second, drifting with the wind. And at nighttime, we we use our ratchets instrument, and we actually reel down 2 kilometers below the balloon, or sorry, below the gondola, and we probe that atmosphere, and then we retract. And we do this, 3 to 4 times in one night, and it takes about 2 hours to do a complete profile. And so in this little subgondola, we have temperature and pressure measurements. We have a hygrometer. So this is measuring water vapor, how much water vapor is in the atmosphere. We're looking at aerosol particles. And then we have a GPS on that, so we know where this profiling unit is in flight. And it's really, crazy idea, because it's a pretty complicated operation, really, because we're taking this. I don't know how to describe it, but it's very exciting, I guess. You can tell I'm excited about this instrument, and it's really neat because it's made with very light parts. So, for example, we have this reeling system that is modeled off of a fishing reel. So it's really just a fancy fishing reel that's dropping this sub gondola, 2 kilometers, and then reeling it back in. And actually, I have a little video of it in operation. And this is all made with all carbon fiber impregnated 3D printed parts, plastic parts. And so inside the gondola, this is what will be happening, 3 to 4 times a night.
Do you think you're going to have any issues with ice, like at the point where the filament is coming in and out of the gondola?
Yeah, so when we did this in 2019, we actually did have icing, because what happens is, when this balloon's first launched, it goes through storm clouds, and so or through clouds anyways, and so it does take on water. And when we first launched this thing, we thought it wasn't working because we couldn't do any profiles. But then as that ice sublimated, in the profiling unit broke free, and we were able to make profiles again. So okay, so then the next instrument is floats, and this is actually really my instrument that I've been working on for the last few years, and this is the fiber optic laser operated atmospheric temperature sensor, which is a little convoluted as an acronym, but floats. And the idea here is that we're using distributed temperature sensing with a piece of fiber optic cable that hangs below the balloon 2 kilometers. It makes temperature profiles 1 meter at every meter interval along that piece of fiber optic cable. And this is this distributed temperature sensing is a little more common in maybe the oil and gas industry, or used in different applications. And it's really unique because this is one of the first times this has ever been used to measure temperature in the atmosphere. There's not really very many good diagrams. I had to steal this diagram, oops, sorry, on how this works, but essentially we're pulsing laser light, infrared laser light down a piece of fiber optic cable, and then there's backscattering that's in the Raman spectra, backscattering from the glass lattice itself that is dependent on temperature. And so, this is just an example figure here from a tethered balloon test that I did, where I was going from the ground and then 1,200 meters into the atmosphere with this system. And this is the kind of thing you can see. It's not perfect right now, but where we have, a pretty cool atmosphere, and then it warms throughout the day. And so, yeah, it's a pretty exciting instrument. And in fact, I flew this a couple weeks ago from a zero pressure balloon and got some really interesting measurements in the lower stratosphere. Okay, so those are the 2 instruments. Next, I'll talk about the field campaign that happened in 2019 and into 2020. So in November and December 2019, we went to the Seychelles for our field mission. And for those of you who, like me, didn't know where the Seychelles were when you first heard about them, it's this little island chain off the east coast of Africa. And it really is like, it's paradise, but it's about -2 degrees latitude. And we launched from this island called Mahe, which is the biggest island in this island chain. And here's just some pictures from the campaign itself. So here's some of the different scientists I worked with. This is our field site. This is a tent where we, we're building up all of our instruments for flight. This is one of the views from that tent, which is very beautiful. And then this is some of the team of people that I was working with from CU Boulder. Also very exciting are the fact that there's flying foxes there. So some of the biggest bats I've ever seen, just flying around everywhere. So when we went to the Seychelles, really none of these instruments had been on these, inside of these gondolas together. So, these different gondola configurations had different instruments in them. And so we had to basically build up all these gondolas, test it out, make sure it's all compatible with our different systems, and then get it ready for flight. And so here's what Ratchets looks like inside of its instrument gondola. This is the profiling unit. So this is what was probing the atmosphere 2 kilometers below the gondola. And then this is what it looked like, finally packaged up and ready for flight. Floats, same thing, much more complicated integration though, because for some reason, someone decided that my delicate fiber optic cable should run through another instrument and then dangle, below that. And so because I didn't want the fiber to break, it made the entire integration very complicated. And in fact, the launch was very complicated too. And the fiber did actually get tangled on this instrument in flight. So that kind of a sad story is this instrument wasn't fully tested in this campaign because it got tangled on the instrument. So then here's a video of the launch of Ratchets. And so this is the French ballooning team here. This is the French Space Agency's ballooning team. And these guys only launch balloons. That's like their whole thing. I guess they used to be on a rugby team and, they run around and lift heavy things. And this balloon, you'll notice, is very crinkly because it's very thick plastic that is being used for these superpressure balloons. And yeah, so that's just an example there of one launch, and there were 8 of those when I was in the Seychelles.
It swings around a lot, huh, with all that package, that load on the end.
Yeah, it really does. It oscillates a lot on the way up. It's like a pendulum until it hits float altitude. And so 8 of these balloons were launched. 5 of them had science payloads on them. And this is just, from November to the middle of January of 2020, this is where they flew to. So these are the 5 different gondolas, science gondolas. And I think I made this figure when one of them was the first to circumnavigate the world. So it was pretty exciting. And, and so one of the things we were really not sure about is, how do these balloons really, fly? How do they drift around? How do they interact with their environment? Because really the idea here is we're sampling the same air mass as, in place as we drift along. And we want to know how it changes as we as we make our measurements. And so here's a little video I put together that has, this is from the Ratchet's flight. We have altitude, so this is our altitude with respect to longitude here. And then this black line is the same. This is our flight track on a map with brightness temperature from satellite data, which is really an indicator of convection. So where are these big storms and thick clouds? And then here is the so this is the cloud top estimate. So this is about where, what the height of these clouds are getting to. So if it's really dark red, that means those clouds may be getting to about our flight altitude, because, the max in this analysis was about 16 kilometers. And so just follow along real quick. And it's kind of cool to see, what storms in how different circulation patterns, affect our balloons in flight. So you can see here, we're flying over Indonesia, and then big storms pop up, and we fly right along with these storms. And then what's happening is, because we're in a storm right there, we actually descend. We're in a storm, and there's very cool air around us. And so the helium itself cools, becomes less dense, more dense, and it actually descends about 1.5 kilometers in flight. And then it just follows along these storms. And then eventually, I'll just fast forward some, it gets kicked out of these storms and no longer follows them. Okay. So then, so for Ratchets, I mean, it was a very successful flight. We had around 50 useful profiles, but 67 total profiles, up to 20 meters below the gondola, of temperature, water vapor, and aerosols. And this is something that's never really been done before. And we sampled, all around the world, and really actually saw some interesting stuff, mostly above the continents. So the maritime continent here, Africa, and then over the Amazon rainforest. And this is what the data looks like. So here's just our position of the green is the gondola itself, the balloon gondola, and then our profiling unit, descending, dwelling at the 2 kilometers below, and then ascending. And so for each profile, we're actually getting two, we're getting the, I guess for each sounding, you could say, we're getting 2 profiles. So we're getting an ascent and descent. And it's really useful because they're, one's upwind from the other. And so you can see how some things are changing with the passing of time. And here's what the, what just temperature, aerosols, and then water vapor are looking like in just one profile. And so what you can see is this cold point right here. So 186K, I think is, what is that actually? Like it's like -90 something Celsius. We're seeing, so a very cold point right there. And then we're heading into the stratosphere here. And, with our aerosol counter, we're seeing some particles in different spots, which we are attributing at this point to subvisible cirrus clouds. And then, we get a nice water vapor profile. And so we have around 50 of these that are, that we can analyze. And so just quickly, how does this compare to, other, how good were these measurements and how do they compare to other sort of measurement options that are out there? So, taking the water vapor profiles and comparing them to the MLS, which is the microwave limb sounding satellite that measures water vapor and I think temperature it does pretty well. So we compared our water vapor instrument compared very well to MLS. And then, just comparing temperature to other sources of different temperature measurements, surprisingly, there's not a whole lot of meteorological soundings in the tropics. And in fact, I did some research into this, and we really only had coincident meteorological sounding measurements with our balloon profiles, or somewhere around like 10 times. And the only ones that had available data were these ones over South America. And so just, looking at this one, we compared really well to meteorological soundings. But yeah, so ultimately there's still, we're a year into having a bunch of really good, interesting data to look at. And there's a lot of analysis that's going on right now that I, don't have time to show. But there's some really interesting stuff that's coming out of this project. And then, we're really excited. So in, only 6 months or so, we'll be going to the Seychelles again and launching 3 times as many of these instruments, and getting lots of, great data. So I guess, yeah, with that, I'll take any questions you have.
I know this is like a little bit out of the realm of like the scientific stuff that you were talking about, which was very interesting. But with the balloon, do you know if they've ever like considered using a more like biodegradable material?
Yeah, I don't think so. I mean, at this point, biodegradable plastics aren't really as good as petrochemical plastics. Plant-based plastics aren't really there yet. So I mean, it's a possibility in the future, for sure. But ultimately it does suck that we're dropping a ton of plastic into the ocean, but ultimately this is a lot less wasteful than a lot of other things that happen in the world. And and this is really for climate science. Everything we're doing ultimately is going to improve our climate science. So, there are trade-offs for this sort of thing.
So Doug, can I play off of that last comment, which is about climate science? And I want to pan back into a greater global consideration of environmental concern. I'm thinking that our tropical coastlines are almost becoming uninhabitable. And by that, I mean, we're seeing more super hurricanes that are stronger than Cat 5. It's time to define a Cat 6. They're coming around more and more often. We had, I think, a Cat 6 hurricane in November this year, and it hit the Philippines again. So you have communities that are getting hit by massive storms before they've had time to rebuild from the previous one. And it's resulting in a lot of climate refugees. When their entire community is trashed, they have to leave for a while. So my question is, in the notion of climate science, do you have any comments on the interplay of your efforts to better understand the atmosphere and this huge concern that I have about the storminess of planet Earth?
Yeah. Well, ultimately the measurements we're making, they're interesting from a pure science standpoint, understanding the dynamics of the TTL, and from the, understanding the, dynamics of the lower stratosphere, that sort of thing. But what we're really doing is improving models. So, there's all sorts of atmospheric models out there. They're telling us, what is our weather going to be like today? Or, what is the climate going to be like in the future? And this is really, playing into that. If we can understand something like these subvisible cirrus clouds, okay, they and where they're at, where these subvisible cirrus clouds are, how many there are, how dense they are, things like that, we can really improve these climate models, because these cirrus clouds are reflecting sunlight and absorbing sunlight at different rates. So they have direct and indirect effects on solar radiation. And so in these ways, I think we'll be able to say a lot. But ultimately, how it goes into the climate science isn't really my field. So that's for other people to do. They can take my data and use it. And a lot of people will, in fact.
Any other questions?
Yeah.
Is there a reason that NASA is not part of like this?
No, not really. Just that they weren't involved from the beginning. NASA's got their hands in a lot of stuff. I'm actually part of a separate NASA project looking at outflow into the stratosphere, pollution outflow into the stratosphere from the Asian continent. And there's most people that are involved in NSF or NASA, they're involved in both. And this has just happened to be, they weren't part of the funding for this, and they're not really needed for any of the ballooning stuff. So. Any other questions?
I have a question.
Thank you very much. You too.
Mm-hmm.
Oh, sorry. How do you go about breaking up the data? Because when you say your balloons circumnavigate the world, like I can only imagine how much data you guys are collecting. So do you break it up by every mile or every continent, or I don't know, I'm confused.
It's complicated. I mean, right now, so with like the Ratchets instrument, we break it up by profiles. But then, looking at different parts of the atmosphere, the atmosphere above the ocean is very different than the atmosphere above the continent. So then we can divide it up that way. And then there's other ways too. Whether it's dark or it's light out, is the sun out or is it down, or are we near storms or not near storms? So it's still, honestly, it's a very complicated data set, and you're right. It's not an easy assignment to do. So.
What I find so fascinating is the difference between the tropopause and stratosphere interactions over the tropics versus the mid-latitudes, where you have these really well-defined stratospheric intrusions and in the mid-latitudes, and then the tropics it sounds like it's a free-for-all.
Yeah.
It's going to be really interesting. You're mapping that tropopause layer will be really cool.
Yeah, exactly. Yeah, I mean, that floats instrument, it was really disappointing that it wasn't able to be operational in flight. Because that would have been really easy data to be like, because we have continuous temperature measurements, 2 kilometers. So in that, thermal tropopause area for the entire flight. And it would have been so interesting, really, and really easy then to map, like and to characterize this layer. But, we'll have to wait until the next campaign to do it.
Yep.
Mm-hmm.
All right. Does anyone have any other questions? If not, we'll let Doug go. Thank you so much for taking the time to hang out with us. Really appreciate it. Are you comfortable with putting this on our YouTube channel?
Yeah, absolutely.
Okay.
Go ahead.
Fantastic.
Yeah.
That's awesome. So, because we have a lot of students who have class from 12 to 1, so then they watch it on the YouTube channel afterwards. So.
Oh, okay.
Yeah, thank you. That was fantastic, and it was so great to see you and catch up.
Yeah, thanks. Yeah, it was great. Thanks for inviting me to this talk. So.
Okay. And yeah, check out the YouTube channel. Seth is on there, and Matt's gonna be up in a couple weeks, and Dan Cannon's gonna be on. I don't know any of those names for familiar for you, but
Oh yeah, they're familiar.
yeah.
Yeah,
All
that's a
too
few
familiar.
all-stars right there. Yeah.
Oh, that's right. All right. Well, thanks again.
Okay, thanks everyone.